Welcome back, ladies and gentlemen. In this video, we'll look at series and parallel circuits and apply Kirchhoff's laws to solving circuits. Okay, so this diagram on your screen, please pause, please draw this. We are going to add to this big drawing as we go. This is what I will refer to as a circuit puzzle. And I'm going to start with the end in mind. This is a combination circuit, one that we'll cover in more detail in our next video, but it will serve as talking points for many of the topics that will pertain to solving circuit puzzles. So first of all, when we say solve the circuit puzzle, that means to find the current in each branch. So current flowing in a circuit, current first of all is indicated by arrows, 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 and that just indicates the current is flowing in a certain direction. Each branch just means each line, or I guess branch, that current will be able to flow. Okay, we are going to look for the voltage drop across each resistor. So each resistor will have values attached to it: voltage, resistance, and current, which of course we know that we can use to use Ohm's law. If we have two of those values, we can solve for another one. So our goal is to be finding the voltage drop across each resistor. We're looking for the resistance in each resistor. In this case, our resistance values are given to us. Our resistor number 2 should also point out that each resistor will have its own set of values, right? So each one of those values pertains to the resistor that it's next to, okay? And then finally, we'll look for the power in each resistor, and that'll be a bit of an add-on for us, okay? So before we get into this, we're just going to talk about a little bit of recap. So recap, this is a simple circuit that's on your screen. We've got a battery that's providing movement of electrons over to a resistor, and then we've got an ammeter and a voltmeter. So this diagram that's up in the top right corner of your screen, that is going to disappear in a minute because this screen will get busy with the information that we'll talk about. But the first thing that we'll talk about is moving charges. This is current electricity. When we talk about current electricity, we talk about electrons or charge moving in a couple of different ways. The first way is with the red arrows on your screen, and that's where charge is flowing from the positive to the negative. And on your battery on your screen, the long line that is indicated on the battery will always represent the positive side of the battery, and the short line will be our negative side. Conventional current is one that is going to flow out of the positive, and we call it conventional because Ben Franklin, back in the day, studying electricity, thought that a charge flowed in out of the positive terminal. Of course, he ended up being wrong, but still to this day we talk about conventional current because he is the father of finding or talking about this stuff in a scientific way. Okay, so this diagram will, in the top right, will disappear, and then we'll just populate and talk about some other things that are happening in a very simple circuit. Okay, so we have moving charges. We talk about those in units of coulombs. And there's Ben Franklin. He's saying that, oops, he got the direction wrong. There's another, just drew another arrow on there saying that, hey, moving charges, this is just talking about electron flow. Okay, so it doesn't really matter which direction you use or indicate on diagrams when solving circuits. I will use the conventional current direction and draw my arrows for current from the positive, out of the positive side of the battery. Okay, next up, we have an ammeter. That ammeter is drawn in series. We have to run electrons through that ammeter so that we can pretty much do a count of how many coulombs or how much charge is passing per second. Okay, next is the resistor. Remember, the resistor is really, its whole purpose is to slow down electrons. We also talk about, or we will draw electrical loads as resistors. Electrical loads are things like a toaster, computer, things that we plug into the wall, and those are just items that convert electric potential energy into another form: heat, light, motion. Okay, so we have a resistor, just the idea that those charges are going to lose electric potential energy as they go through a resistor. Okay, the whole idea of a battery is to give the charges energy. And they get that energy so that they can move around the circuit. Okay, and then there is a voltmeter, and the whole purpose of a voltmeter is to measure the energy gain or loss as it goes through a battery or an electric load. So when we're talking about gains, this will be electrons that are traveling through a battery. For instance, we could put another voltmeter across this battery like so, and that would measure the energy gained by each coulomb. This voltmeter that's over on the side here measuring the energy loss is energy lost going through a resistor. Okay, so just an analogy that we can think about going around a circuit is like a bank. And the whole idea of a bank is, in this analogy, is the bank is just going to give customers money to spend. Then the bank is going to say, hey, customers, go out, run around the block. You have to spend your money at a store and come back to the bank for more money. Okay, so people go running out of this bank, and people are like the charge, like the electric charge. They're out just spinning around or running around the block. There is a little turnstile here. That turnstile is going to measure the rate of customer movement. So that's just how many customers pass in a second, is our analogy for an ammeter. Okay, the store, that is where the money gets spent. So we are going to take our money and turn it into something else, candy, or a new pair of shoes, or you pick your item that you're looking to spend your money on. Okay, and then this guy, he's our wallet inspector. He's really just checking out. He's doing a little check before the bank, before the store and after the store, and he's just checking, hey, how much money do you have here? And if it's, I don't know, like a 9-volt battery, you can say, hey, wallet inspector, I started with $9, and down here I ended up with $0. So how much money did you spend? Well, you spent $9 or 9 volts going through that store or electric load. Okay, so voltage is a tough one to understand, but it's really just about it's the amount of energy that each of those charges have. Okay, so we will get into questions where we have a series circuit, and the series circuit is where we are going to have 2 stores where we have to spend our money. Ooh, and that's another key idea here, people, is that by the time you leave the bank, run around the block, spend your money, and come back to the bank, you are always going to come back to the bank broke. So if you leave that bank with $9, you're going to come back broke. If you leave with $1,000, you have to spend all that $1,000. It's a good problem to have, I guess. You have to spend all your money before you end up back at the bank to top up your funds that you're going to go spend again. Okay, so this is like electrons. Electrons come back to the battery. They get some electric potential energy, and they go and spend it in an electric load or a resistor. Okay, so when we have a series circuit where we have, here we have 2 stores, and I've called these stores McDonald's and Boston Pizza because we know that, if you have money to spend, choosing where you eat is going to, a price is going to be a big determiner of it. So if we again leave this bank with $9, we have to come back into the bank with $0. And these 2 restaurants are different, right? So I just want to point out that our voltage drop, or the amount of money that we spend in each store, or the amount of energy that we lose in each load, might be different. And that's okay. But the idea is that you have to spend all the money before you go for a top up of, in this case, another $9. Okay, so that's just a little analogy. So if you hear me talking about spending money, it's just our money spending, or the bank analogy, as we're ripping around a circuit. Okay, so back to our goal of solving the circuit puzzles. We are going to find current, voltage, and resistance, and then power as an add-on. Okay, so some tools that we are going to use to solve these circuits. One of these tools we've already used, and that is Ohm's law. Okay, so if we have 2 of these values, we can find the third by using Ohm's law, okay? And when I say two of these values are the values that pertain to a certain resistor, okay? The other rules that we will use, or the tools, sorry, that we will use are Kirchhoff's current law, which is the law of junctions, and Kirchhoff's voltage law, which is the law of loops, okay? So first of all, just to comment on Kirchhoff's laws. Kirchhoff's laws are named after Gustav Kirchhoff, who was a German physicist, lived in the 1800s. He did lots of work with our fundamental understanding of electricity, which is why, of course, he has laws named after him. He also studied spectroscopy and the emission of black body radiation, which I believe, just from a quick Google search, he actually termed or coined that phrase, black body radiation. Okay, so Kirchhoff's current law. I've now put currents onto the circuit on your screen. Okay, this IT means total current. Total current. We talk about total current as the current that runs through the battery in our circuit. Okay, so in this circuit, the total current running through the battery is 2 amps. So 2 amps leave this battery and it comes around and it hits this, what we call a junction point. Junction is where you have conductors that come together and electrons really just get a choice of where to go. So when we talk about junctions, we're talking about, I guess, choice for electrons to move. Okay, so you will notice in here, as current comes into this junction, if 2 amps are coming into this junction, we have then 1.5 amps that is running through resistor 1. We have 0.5 amps running through resistor 2. You add those two values together and you get 2 amps. So the big idea with Kirchhoff's current law is that at any junction, the total current into that junction has to equal the total current out. Okay, and that all has to do with the conservation of charge. We can't have charge that just disappears, or electrons or coulombs that disappear as they are going into or out of a junction. Okay, in short form, just I in equals I out of a junction, or current into equals the current out of a junction. Okay, as you can imagine, our next Kirchhoff's law is going to be the voltage law, and that's the law of loops. Now, loops are really just talking about a total path from the battery through a circuit and all the way back to that battery. Now, here is one loop that I have drawn. Okay, so if each charge starts with 40 volts of charge, as you go through the loop that I've drawn, if you add up the voltage drops around the loop that I have drawn, 12 plus 4 is 16 plus 24 is 40. So the voltage gains, which is our 40 volt that we've gained through the battery, is going to be equal to our voltage loss, which is the voltage drop as electrons move through resistors. And you can choose any loop you want, right? Like you can choose another loop. Let's see if I can erase that line and choose, in this case, let's choose a different loop. This time we'll send the electrons this way and then this way and all the way back around. And you can play around with that and just add up the voltage drops as those electrons move around any loop. They have to be moving, I guess, you can think of it as moving forward or in the direction that arrows are indicated on your screen, as long as your electrons are moving forward. And what I mean by that is you can't have electrons that come into a loop and then all of a sudden start going around in circles. They don't do that. They want to always get back to the battery to get more money, more juice, more energy. Okay, so Kirchhoff's voltage law states that around any loop, the total voltage gains come from a battery. That is going to be equal to the total voltage lost across electric loads. Excuse me, as electrons go around a loop. And that has to do with the conservation of energy. Okay, energy cannot be gained or lost as electrons rip around a loop. Okay, in short, V gain is equal to V lost around a loop. And again, whenever you hear me talk about V gains, this is from a battery. Whenever you hear me talk about voltage lost or voltage drops, this is around electric loads or resistors. Okay, so next up, just talk about series and parallel circuits. So I'm hoping that you've seen these things before in Science 9. Series and parallel circuits are just circuits with more than one resistor or electrical load. Okay, we are going to, here's a quick look at a little GIF that shows electrons moving around both the series and a parallel loop. Parallel loops are definitely more commonly used for us. Our homes are wired in parallel so that if all of a sudden this light bulb or electric load goes out, then electricity will still flow to the other things or loads that are on that circuit. Okay, so we'll talk about the key points between each of these two types of circuits. Okay, so in series circuit, there is only one path for electricity to travel. Current is the same everywhere. So in this battery, I'm just going to label my positive and negative. That will be convention or things that we do later. I'm also going to indicate the direction of my current. That is, again, something that we will do later. Current is the same everywhere. So if I were to say, hey, in this loop, this has 2.0 amps. Well, if I were to put an ammeter right here, and an ammeter right here, you can now tell me with certainty that, hey, all of those ammeters are all going to read 2.0 amps. Current is the same everywhere. Okay, the same number of charges is going to be going through that ammeter everywhere in that circuit. Okay, if one light goes out, the circuit is broken. Again, that's why we don't really use these in homes because, well, we have many lights or many loads that are attached to one circuit. And then as we add more loads, it increases the resistance and decreases the current. Okay, and we quantify that with the following formula. An REQ is just equivalent or equivalent resistance. RT is just total. So those two words are the same for series circuits. That one's pretty easy. We just add up the resistance. So in the circuit, we'll talk about collapsing circuits or reducing circuits. I can then take those three resistors and draw a much more simplified version of this circuit and just replace all three of those resistors with an equivalent resistor. So if R1 was 5, R2 was 7, R3 was 8, then our equivalent resistance in the circuit would be 20 ohms. Okay, that's a tool that'll come in handy for us when we are solving our circuit puzzles in later questions. Okay, so here's a quick example. Find the missing voltage value. Okay, we have a 120 volt power source. I'm going to label my positive and negative sides. Again, the positive on the battery is the long line. The negative on the battery is the short line. So if I'm given $120 to go out around the block, and at the first store I spend 80 of it, how much do I have to spend at the second store? Well, I have to spend 40 volts. Okay, so a little bit of problem solving and math to find out what that missing voltage value is going to be. Okay, and another one. Okay, if we have, this time we're given 12 volts and we're asked to go around circuit, we spend 4 volts in one store, 3 volts in another. Well, this missing voltage value has to be 5 because as we leave the battery with 12 volts, we have to come back into the battery with 0. We have to spend all of our money before we come back for a power up at the store, at the bank. Sorry. Okay. Parallel circuits. Parallel circuits are where electricity has more than one path to follow. So electrons get a choice. So positive and negative side of our battery. I'm always going to draw my current from the in the conventional fashion. Okay, so this is where electrons will come around to a junction point and then they get to make a choice which way they are going to go. Okay, so For parallel circuits, the voltage is the same in each branch. So what that means is if we have a power supply of 12 volts, that means that the voltage through R1 is going to be 12 volts. The voltage in R2 is going to be 12 volts. And then, yep, you guessed it, the voltage drop across R3 is going to be 12 volts. And this is just Kirchhoff's voltage law, right? Where we start the battery, we go around this one loop, okay? And if we get 12 volts of energy, we have to spend that 12 volts through the resistor that we've gone through in that loop. Okay, if we choose a different loop, go through our second resistor, we still have to spend that 12 volts. And then of course the third branch would be the exact same. Okay, this is how our homes are wired. Sorry, I'll keep going with the points here. So current in equals current out of a junction point. That's just a repeat of Kirchhoff's current law. Okay, adding loads decreases resistance and increases the current. I'm going to do a quick flip over to FET and show you what that looks like. This is a crazy looking FET setup where we've got a battery voltage of 15 volts. I've made each light bulb 10, then 20, and 30 ohms. And this is kind of like the setup in your house, right? Where you've got different lights all on the same circuit. This ammeter down here is really the total current. That is the current that is flowing through the battery. So what I'm going to do is I'm going to go up and close this light switch up here, and I want you to watch what happens to the total current running through this circuit. Okay, and it's key that we understand that as we add more loads in parallel, so I'm going to close this circuit. We start at 2.25 amps, close this circuit, and all of a sudden we have more current running through it. So when you are wiring things in a home, that's why there are very specific rules for how many different outlets or light bulbs or fridges or other electric loads that you can put on a single circuit. And remember, in your home, each circuit is tied to a breaker. So there are limits to how many electric loads you can put on each circuit, because as you put more and more loads, you add more current to that circuit, and eventually your breaker will trip. And if you didn't have a breaker, eventually your house would burn down with too much current flowing through it. Okay, so as we add more resistors or loads in parallel, resistance, our overall total resistance decreases and our current increases. Okay, so if we quantify that, the formula for this one gets a little more complicated. So hope you have your calculators ready, because we will go and just try and see what this will look like for us. So here is each one is 1 over, so 1 over REQ, or equivalent resistance, or total resistance. We're going to add up 1 over each of our resistor values. So if I said your resistor value was, I don't know, 10, 20, and 30 ohms, how we would solve that is this. So if we're looking for the total resistance of this thing, we're looking to take this circuit that looks like so, and we want to move it into a single equivalent resistance. So we'd have to go 1 over 10 plus 1 over 20 plus 1 over 30. Okay, and now the tricky part with your calculator is to find a really handy button is the 1 over x button, or on your calculator you might have an x to the -1 button. Okay, so on my calculator I'm pushing 10 1 over x plus 20 1 over x plus 30 1 over x, and I get 1 over RT is 0.183 repeated. And then I have to hit the 1 over x button one more time, and that's going to give me an equivalent resistance of, or a total resistance of 5.45 ohms. Okay, so that's just a quick example about how to find total resistance for a parallel circuit. Okay, So couple more small examples here. So we have the total resistance. This will be a question that comes across in your problem set for this lesson. Total resistance or equivalent resistance in a circuit that looks like so. So our first step here is going to be to deal with these two resistors, and we're going to turn this question from what you see on your screen to this. We replace those two resistors with the one unknown. So we know that these are parallel resistors. So to find this equivalent resistor, we can use our parallel formula, which is 1 over R1, or 1 over 12 plus 1 over 6. Okay, and if I do the math on that, 1 over Req is then going to be 0.25, or R equivalent is 4 ohms. Okay, and then one last step, we now have a series circuit with 3 resistors in there, 9, 4, and 5, and the series equivalent resistance for a series circuit is a little easier, where we just add them up. So 9 plus 4 plus 5 is, 18 ohms. Okay. So those are types of questions that you will see in your problem set. I'm actually going to save this one for the next video, and your problem set are 7 questions from pages 471, 474, and 477. Thanks, ladies and gentlemen, and we'll see you again soon.